what we've looked at previously is the addition of two spin half angular momentums. So a quick recap. We have two spin half particles. This means that S1 equals 1/2 and S2 equals 1/2. And if these spins were interacting, which also meant that they were that this interaction could be described by a certain Hamiltonian, which we defined as 2a over h bar squared S1 dotted S2. Then we were able to find the eigenstates of this Hamiltonian, the eigenstates and the eigenvalues. The eigenstates and the eigenvalues turn out to be the following. Of course, it's a four-dimensional space, so the eigenstates, the number of eigenstates would be 4, and they're given by ket z, minus z, so 1 over under root 2 z minus z plus 1 over under root 2 minus z, and then there is 1 over under root 2 z minus z minus z. Alright. So these were the four eigenstates of this particular Hamiltonian. And what I've done here is that I've written these eigenstates in a certain basis. And the basis that I've chosen is the set of four states z, minus z, and minus z. So here I've written the eigenstates in terms of these four basis states. Okay. And another interesting observation is that we made in the previous lecture was the following. These four states, which are the eigenstates of this interaction Hamiltonian, which we call the hyperfine interaction, correspond to certain values of the total angular momentum S and ms, which is the azimuthal component of the total angle. This state, for example, corresponds to S equals 1, ms equals 1. We also label this state as T1. This state corresponds to S equals 1, ms equals 0. We also label this state as T0. This state is really corresponds to a total angular momentum of 1 and ms of minus 1. We label this state as T minus 1, and this state corresponds to S equals 0. And corresponding to S equals 0, there is only one possibility of ms, which is ms equals 0. And we label this state as S0. These three states we call the triplet state, and this is the state that we call the singlet state. So now, what we've noticed is that the eigenstates of this Hamiltonian are the singlets and the triplets. Alright. Now, which means that it is possible to define another basis for the Hilbert space. Remember that the basis is independent of the Hamiltonian. The basis just depends upon the Hilbert space. However, sometimes it becomes convenient to work in certain bases than in others. So if you look at this Hamiltonian, this hyperfine interaction Hamiltonian, the states, the eigenstates, this is one possible set of eigenstates. The eigenstates are independent of the basis. So this state is the same as this state. This state is the same as this state. All of these states are equivalent. They are just different representations of the same state. Hence, it is possible that we can choose any basis that we like. One possibility is to choose this basis and this basis, that is. This is called the direct product basis. And each of these states actually corresponds to a direct product between Zenon states. For example, this is really ket z tensor to z. This is get Z tensor with minus Z. This is minus Z tensor with Z. And this is minus Z tensor with minus Z. So this is called the direct product basis or the uncoupled basis. Okay. Another possibility is to choose the set of states T1, T0, T minus 1, S0 as our basis. Okay. So this is an equally legitimate basis for the four-dimensional Hilbert space, isn't it? Alright. And what's so special about this basis, which is called the coupled basis? The speciality about this coupled basis, which really means the convenience of working in this basis when we're dealing with an interaction Hamiltonian of this kind, is that the states correspond to precise values of the total angular momentum and the Z component of the total angular momentum, which means that if I were, which also means that these states are the states of the total angular momentum, S squared. So if I take S squared and I act upon this, the triplet state, okay, any triplet state, I will get H bar squared. S is 1/2. 1/2 into 1/2 plus 1 is 3/4 under root. So under root 3/2, I get 3/4 and the corresponding state, which means that the triplet states are eigenstates of the total angular momentum squared. But these direct product states, the individual states, are not eigenstates of S squared. Only these two states are eigenstates of S squared. Or what about is this state an eigenstate of S squared? No. So this state is also an eigenstate of S squared. But what about this state on its own? Let's see. Is this state an eigenstate of S squared? So if I take S squared and act upon it ZZ, then this really means S1 squared plus S2 squared ZZ. Is this an eigenstate of S1 squared? Yes, it is. It's also an eigenstate of S2 squared. So these direct product states are eigenstates of S squared. However, likewise, if I have SZ and I act upon it, act this upon the triplet state, right? I get back the triplet state with HMS. MS now depends upon this quantum number. If it's 1, this is 1. If it's minus 1, this is minus 1. If it's 0, it's 0. So the advantage of working in this coupled basis or the singlet triplet basis, this is also called the singlet triplet basis. The advantage of working in this basis is the following. If I were to write Hamiltonian in terms of the singlet triplet basis, what kind of matrix would result? The 4/4, but any special properties of this matrix? It's going to be diagonal matrix. And what are the elements of this diagonal? What are the eigenvalues? The eigenvalues we found out the other day. A over 2, A over 2, minus 3A. Okay. So this is the interaction Hamiltonian, the hyperfine interaction Hamiltonian in singlet triplet basis, where we have labeled, ordered the states in the following way. This is T1, this is T0, this is T minus 1, and this is S0. Okay, this is T1, T0, T minus 1, this is S1. Remember, we also have to choose an ordering of the states when we would like to write any matrix in a particular basis. Okay. So in this ordering of states, this is the Hamiltonian. Okay, so the Hamiltonian is diagonalized. So if the hyperfine interaction acts as a perturbation on a background Hamiltonian, okay, and we recognize that we can write this perturbing Hamiltonian in any basis, and the eigenvalues will be the corrections to the energy. So if you write the hyperfine interaction in terms of the singlet triplet basis, these diagonal elements will just give the corrections to the energy. And this is one homework problem that I have already given you. Okay. So if we look at this singlet triplet basis here, we can make an interesting observation. That is, if we take this state, this has the maximum value of ms corresponding to this s. Okay. Then we can generate this T0 state from the T1 state by having the lowering operator act on this state. So if the lowering operator acts on this state, we generate this state. Because S does not change, the Z component is decremented by 1. This is what the lowering operator is. Doesn't it? So if I make the lowering operator act on this state, I will get this state. So by repeated applications of the lowering operator, I can decrement the value of the Z component of the angular momentum by 1. Whereas I will not touch the total angular momentum quantity. Okay. Now if I would like to go from this state, up to this state, I cannot use the lowering operator because this value of S is different from this value of S. So I will have to use some other property like the orthogonality condition, which means I take this state and I take this state. Both of them have the same value of ms. Right? So I can get this state from this state by invoking the orthogonality condition. And this is another homework problem that I will do. It is all of these 4 states must be orthogonal. Okay? Now, I would now like to generalize all of this. So far we've been dealing with 2-spin half system, but what's the generalization? And what do I want to do? I would like to find the total angular momentum states and the azimuthal components of the total angular momentum states. In other words, I would like to find states. Okay, let me describe this. Suppose I have 2 particles, one with angular momentum J1 and another with angular momentum J2. Okay. In the case that we discussed, this is 1/2, this is 1/2. But J can be arbitrary. It can be any half integer or integer. Right? It could be 0, 1/2, 1, 3/2, 2, 5/2, 3, and so on. Alright. Now I have 2 particles. One has angular momentum J1, the other has angular momentum J2. Now corresponding to these angular momentums, I know that I have angular momentum operators. So I have J1 squared and I have J2 squared. Okay, so there are angular momentum operators. This also means that I have J1Z, and it also means that I have J2Z. And by virtue of these being angular momentum operators, I also know that J1 squared commutes with J1z. J1 squared commutes with actually any component of itself. Okay, this is what we learned in the previous course in quantum mechanics. Likewise, J2 squared commutes with J2z. Okay, these are properties of angular momentum operators. Alright. Now, these operators act on the first particle, and these operators act only on the second particle. This means that any operator J1 squared will commute with J2 squared, okay, and J1 squared will commute with any J2 alpha, right? That alpha is x, y, or z, and vice versa, because these operators act on different spaces. In other words, J1z is a rotation of the first particle about, is a generator of rotation of the first particle about the z-axis, and J1 squared is tells you the length of the angle, tells you the magnitude of the angular momentum of the first particle. That's what J1 squared tells us. Like J2 squared tells us the angular momentum of the second particle, and so on. Okay. So these angular momentum operators live in their own, act in their own Hilbert spaces. Alright, so far so good. Now since J1 square and J1z mutually commute, they will have a joint eigenbasis. Since J2 square and J2z commute, they will have a joint eigenbasis. So the joint eigenstates of these two operators is denoted by J1 and J1. Right? It's given by two quantum numbers, J1 and J1. The joint eigenstates of these two operators, let's label these by J2 and J2. Okay. Now we know from our discussions on angular momentum is that this mj1 can take up values j1, j1 minus 1 all the way up to minus 0. Correct? So there are two j11, there are the number of eigenstates which are joint eigenstates of these operators is 2j1 plus 1. Correct? Alright. Likewise, mj2 can take up the values j2, j2 minus 1 all the way up to minus j2. And the number of possible values, which is the number of these values, is simply 2j2 plus 1. Okay. So now we have joint eigenstates of the angular momentum operators on the first particle and angular momentum operators of angular momentum eigenstates of the angular momentum operators on the second particle. So if we take the dot product of these states, the direct product of these states, J1 and J1 dot with J2 and J2, then these are called the direct products. Okay. Now these could also be written as J1 and J1, J2 and J2. Right? Different authors would try to write this differently. For example, some authors would write these states as J1, J2, MJ1, MJ2. Okay? Some would put a semicolon here, some would put colons here. So there are different ways of writing these direct product states. Now the states that will be written for the two spin half particles like ZZ is really a direct product state. It means Z tensor with Z. It really means two spin half particles, half, half, crossed with half, minus half. Where this label is S, this label is M. this is S and this is ms, right? So the states that we've written, the z, z, z minus z, minus z, z, minus z, minus z are really direct product states. Okay? And remember, what have we done here? What we've done here is that we have chosen a coupled basis and expressed this in terms of the uncoupled basis states. Okay? So this is equal this. There are certain coefficients which are prepended to the direct product states to be this state. Okay? So how do we find out these coefficients? Okay. This, in other words, how would we like to find the total angular momentum states? Because these states are eigenstates of the total angular momentum. Alright. Now if we have the direct product states, we have sets of operators j1 square, j1z, j2 square, j2z, which all mutually commute. Correct? Now if I take j squared and I take jz and I take j1 squared and I take j1z and I take j2 squared and I take j2z, right? Let's take these states. Okay, let's focus on these operators. Sorry. Now if I have two particles, j1 and j2, and they interact with one another, suppose they interact with one another. If there is a j1, an angular momentum associated with this particle, it will have a magnetic moment mu1, and this will have a magnetic moment mu2. Now what does a magnetic moment mean? So there is this is a tiny dipole, this is a tiny dipole, and there will be magnetic interaction between these dipoles. Okay. So if there is some kind of interaction, between, it can change the state of the particle. Now what would I like to see? Now, if there is some interaction between these particles, can this interaction change the magnitude of the angular momentum of the first particle? No. Can it change the magnitude of the angular momentum of the second particle? No. अगर कोई interaction होगा, तो इस angular momentum का magnitude तो नहीं change होगा, क्योंकि क्या होता है? होता ये है कि the torque, if there is interaction, means there is a torque acting on this magnetic moment. That torque is, in classical terms, mu cross B. Okay. Now this torque is dl by dt. Okay, the torque is the rate of change of angular momentum. Just like the force is the rate of change of linear momentum, the torque is the rate of change of angular momentum. Okay. However, this torque cannot change, it can change the direction of the angular momentum, but it cannot change its magnitude. There is no mechanism for the torque to change the magnitude of the angular momentum. So, if the magnitude of the angular momentum, remember the direction can change of the angular momentum, which means that this magnetic moment can change its orientation, but there is no mechanism for it to change
to change the angular velocity or the angular momentum. Hence, under this interaction, J2 will not, under this interaction, J2's magnitude will not change. So this is a conserved quantity. Likewise, J1's magnitude will not change. Okay. Which means that the operator, the observable associated with the magnitude of the angular momentum of the second particle is a conserved operator. And the observable is really J2 hat squared, and this observable is J1 hat squared. In other words, if I take the interaction Hamiltonian, it will commute with J1 squared, and it will also commute with J2 squared. Okay? Because both J1 magnitude and J2 magnitude are constants of motion for the system. So any interaction cannot change the angular momentum of the first particle or the angular momentum of the second particle, the magnitude by the way. Which means that J1 squared, which is the operator corresponding to the magnitude of this angular momentum, is a conserved quantity. J2 squared is a conserved quantity. In other words, both of these operators commute with the interaction momentum. Okay? Alright, so we have these two operators. Let's talk about the total angular momentum. So we focus on this operator and we focus on this operator. Let's talk about the total angular momentum, J squared. Now if there is some interaction between these particles, will the total angular momentum of the system change? No, it cannot change, because the interaction is internal to the system. Therefore, this operator will also commute with J1 squared, it will also commute with J2 squared. Right? Now let's talk about the Z component of the total angular momentum. The Z component of the total angular momentum. The interaction cannot change the Z component either. Why? Because Jz commutes with J squared. And you will notice that Jz also commutes with J1 squared, Jz will also commute with J2 squared. So these four observables, they commute within themselves, and all of them are constants of motion for this interaction. Okay, so these four observables form a compatible set of commuting observables. All four of them mutually commute. Therefore, there are eigenstates, joint eigenstates of all four of these operators. And remember that these observables J1z and J2z do not commute with J squared. You can prove this. Probably you can do it in a homework or if I have Jz, Jz is J1z plus J2. Okay. Now I have to see whether it commutes with J1 dotted with J2. Okay. The J1 dotted with J2 is J1z, J2z plus half J1 plus J2 minus plus J1 minus J2 plus. Okay. Of course, Jz commutes with this. You have to prove that Jz commutes with these operators. And for that, take an arbitrary state. Could be a direct product state. Okay. Take a direct product state and find the action of this operator on the state, find the action followed by the action of this operator. And then reverse the direction, you will see that the order in which these operators apply doesn't matter. Okay. Or you could express J1 plus as Jx plus iota Jy. J2 as Jx minus iota Jy on the second part. And then compute the commutator explicitly. Okay. So now we have four observables, j square, jz, j1 square and j2 square that are mutually commuting. Okay? Which means that all four of them commute with an interaction Hamiltonian of this kind, j1 dot into j, an interaction Hamiltonian that is proportional to this. Okay? So there will be a joint set of eigenstates for these four observables. Let's denote that joint set of eigenstates by j, which is total angular momentum nj. So j and j is a joint eigenstate of all four of these observables. Remember, this is not an eigenstate of j1z or j2z. Okay, let me recap. हमने ये देखा कि if you have an interaction Hamiltonian that is proportional to the dot product of the angular momentum of the first particle with the angular momentum of the second particle, then there are certain observables that are mutually commuting, and each one of those commutes with the interaction. One of them is j squared. The interaction cannot change the total angular momentum of the system. The interaction cannot change the z component of the total angular momentum of the system. The interaction cannot change the magnitude of the angular momentum of the first particle. It cannot change the magnitude of the angular momentum of the second particle. However, the interaction can change the z component of the angular momentum of the first particle and the z component of the angular momentum of the second particle. This means that the operators which I take, all of them commute with the interaction. And you can also prove that any two of these ticked operators also commute amongst themselves. So the observables corresponding to these operators, they are observables corresponding to these operators, they are constants of motion for the system. This also means that these operators commute amongst themselves. It also means that these are compatible observables, which means that you can measure j squared, that is the total angular momentum, the magnitude, and its z component at the same time with infinite precision. That is, if you measure, which means that if you have a system in which you measure the total angular momentum of the system, then it will not disturb your measurement of the z component. Okay. So all four of these form compatible set of commuting observables, which also means that they will have a joint set of eigenstates which are labeled as j, mj. Now what is j? How does j come out from mj? From j1 and j2? Sorry. So j and j are angular momentum states, right? Now these are joint eigenstates of j squared, jz, j1 squared and j2 squared, and they are not eigenstates of j1z and j2z. Okay. Now let's find out what happens when we act these operators upon these states. If I have j squared acting on j and j, my result will simply be h bar squared j plus 1 j and j. Correct? Okay. If I have jz acting on j and j, my result will be h bar nj j and j. Now what are the possible values of nj? The possible values of nj from our theory of angular momentum operators, we know what it is given
given by j minus 1 all the way up to final j. So it decrements by 1. Its extremal values are j and minus j. Okay. Now let's see what happens when j1 squared acts on j and j. Okay, so one has to find out the magnitude square of the angular momentum of the first particle only. That's j1. So because this system, we are talking about the j1 cross j2 system, which means that the first particle has an angular momentum j1, the second one has j2. So this is really h bar squared j1 into j1 plus 1 j and j. Correct? Likewise, if I have j2 squared acting on j and j, this is really h bar squared j2 into j2 plus 1 j and j. Some authors would like to write these states, which are also called the coupled states. Some of them would like to write them as j1, j2, semicolon, jn. Okay. Alright. Now we found out the action of these operators on the coupled states. However, what remains to be seen is what are the possible values of j given j1 and j2. Alright. So we would like to find out the possible values of j. Okay. Now, how do I know that? If I look at this eigenvalue equation, this is an eigenvalue equation. If I look at this equation, I would notice that this jz is j1z plus j2z. If I look at this mj, what's the maximum value of this mj? What's the maximum possible value of mj given some j? J. So the maximum value of mj is j. Okay. And what's the minimum value of mj? It's minus j. Now when can I achieve the maximum value of mj? Okay, now I have two particles. Each particle is angular momentum j1. So this first particle, when its mg is max, now what is this? This is just the z component of the total angular. So it's intuitive that I can maximize the z component of the total angular momentum when each of the constituent particles, its z component is maximum and is pointing in the same direction. So if I have this particle, what is the maximum z component of this particle? It's j1 and its maximum z component is j2. So the maximum value of mj, which is j, is j1 plus j2. Okay. So now this is the maximum value of j that I can get. Okay. The minimum value of mj, which is minus j, is of course likewise minus j1 minus j2. Okay, so this is minus j1 minus j2. So if the maximum value of mj is, which means that j is given by j1 plus j2. Now I have to find out how does j vary. I mean, what are the possibilities of j? So the maximum value of j max is j1 plus j2. And what's the minimum value of J? Now the point is that if I take the minimum value of Mj, this is minus J. Now this is minus J1 plus J2. This is the minimum value of Mj that I can have. So this is simply minus J of max. Okay, which is true. Mj varies from J max to minus J of max. Okay, but this only tells me what J max is. What is my J minimum? I have to find out the value of J minimum. What happens is that J can take up values from J1 plus J2 and it decrements them by 1. So the possible values of J are J1 plus J2, J1 plus J2 minus 1 and all the way up to J1 minus J2's with the modulus, because the total angular momentum quantum number cannot be negative. So if J1 is greater than J2, I just take J1 minus J2. If J2 is greater than J1, I take J2 minus J1. So these are the possible values of J. Now how can I find out, how do I find out this J1 minus J2? What I would like to do is that if I have this Hilbert space for this joint system, its dimensionality is going to be 2 J1 plus 1 into 2 J2 plus 1. Okay. Suppose I have n of these J values. Okay. Corresponding to each J value, I have 2 J plus 1 states. Right? So I can find out the value of n so that the number, the dimensionality of the system becomes equal to this. Okay, and this is another homework problem. So I would like to find out the minimum value of J. Okay. And I pose it or I present it, I say that the minimum value J1 and J2 models. Now I know that the dimensionality of the Hilbert space, of the joint Hilbert space is 2J1 plus 1 into 2J2 plus 1. Okay. So corresponding to each value of J, I have 2J plus 1 values of Mj. So 2J plus 1 into this number M must equal this. Okay, both of these must be equal. But remember, I am starting from J1 plus J2. So I can find out the minimum value of J. Okay. This is something that we should do as an exercise. So if I have two angular momentum states, J1 and J2, and I want to find a total angular momentum, these are the possible values of J. Just as if I have two spin half particles, S half and S half, then I would like to find the total angular momentum. I plus these values 1, I subtract these values 0. And these are the only two possible values of S, and corresponding to S equals 1, I have 3 values of Ms. And I have 1 value of Ms corresponding to this. This means I get 4 states, and these are the same 4 states which I call the singlet and the triplet states, which I have denoted here. Now the point is that I would like to find out these coefficients. Alright. So I would like to introduce to you an example which helps us find out these coefficients. Suppose I have, now if I take up an example, things will be clearer. Suppose I have a deuterium atom which comprises a deuterium nucleus and an electron. So a deuterium is a spin 1 particle.
A deuterium nucleus is a spin 1 particle. A deuterium nucleus comprises a proton and a neutron. So this is J1, and the electron, which is in its ground state, does not have any orbital angular momentum. In the recitation, you see what happens when you have orbital angular momentum as well. So if the electron is in the ground state, its orbital angular momentum is 0. So it only has spin half. Its spin is the total angular momentum. So J2 is half. So J1 is 1, J2 is half. Alright, so I really have a 1 crossed half system. Remember, these are just labels. This is the angular momentum of the first particle and the angular momentum of the second particle. So my allowed values of J are 3 by 2. I add, subtract from it 1 half, 3 by 2 and half. And I don't go further because this is really J1 minus J2. So corresponding to this value of J, I have 4 values of Mj. I have 3 by 2, 1 by 2, minus 1 by 2 and minus 3 by 2. And corresponding to this value of J, I have 2 values of Mj half and minus half. Okay. Now I would like to find out the coupled basis states. Okay, the coupled basis states, which will be eigenstates of the Hamiltonian J, which is proportional to J1 log to J2. Now the coupled basis states are quite simple to write down. They will be denoted by J and J, right? And these are eigenstates of J squared, Jz, J1 squared and J2 squared. Okay. Let me write this down. If I have observables J1 squared, J2 squared, J squared and Jz, then their mutual eigenstates are denoted by J and J. And if I have eigenstates J1 and J1 tensor with J2 and J2, then they are also eigenstates of some observables. What are those? What are those observables? If I take J1 squared, this is an eigenstate of J1 squared. It's also an eigenstate of J1z, because I have specified the value, the z component of the angular momentum of the first particle. And these are also eigenstates of J2 squared, J2z. So the direct product states are eigenstates of this mutually compatible set of commuting observables, and the coupled states are eigenstates of this set of the compatible set of commuting observables. देखो, ये वाली जो states हैं, जो direct product states हैं, these are eigenstates of J1 squared, right? Because when this operator acts on this axis, I have specified the value of J1. It's just going to be h bar squared J1 into J1 plus 1. These are also eigenstates of J1z because I specified the value of Mj. These states are not eigenstates of J1z because this Mj, we don't know the value of Mj1 and Mj2. So these are not eigenstates of, so these states are not eigenstates of this, and these eigenstates, these states are not eigenstates of this set of observables. Okay, is समझ आई बात? So if I have this commuting set of observables, the eigenstates are given by J and J, they are coupled states, and if I have these sets of observables, the eigenstates are given by the direct product states. Okay, that's fine. So if I have the coupled basis states, which are eigenstates of this set of commuting observables, then they will simply be given by, now the values of J are 3 by 2, so I have 3 by 2, comma 3 by 2. So the first label represents the value of J, the second represents Mj. Okay. The next state, which I can achieve from this state, is by the action of the lowering operator. the total lowering operator in this state. Now what this total lowering operator can do is that it creates, it just decrements the value of mj, the total z component, and I get half here. Then I have this j minus operator acting again, I get minus half. Then I have j minus acting again, I get minus 3. Okay. So I have generated these 4 states. Okay. So these are the 4 states in the coupled basis. I also have 2 more states to go. The total dimensionality of this Hilbert space is 6 because 3 by 2
J1 can have 2 values and J2
right.
can have 1 value.
J1 can have 2 values and J2 can have okay. J1 is just 3 by 2. J can have 2 values which are 3 by 2 and half. Okay. So these 4 combinations, I can have 4 combinations of J and Mj corresponding to 3 by 2, and I have 2 combinations corresponding to this half. In other words, 2 times 3 by 2 plus 1 is 4, 2 times this plus 1 is 2, so I get 4 plus 2, 6 states. So the dimensionality of the space is 6. So the other 2 possible states are half, half, and half minus half. Okay, so these are the 6 possible states which span the entire Hilbert space. Sorry?
इधर भी J minus ट्रांजिशन कर सकते हो.
हाँ, इधर भी आपस में J minus ट्रांजिशन कर सकते हैं.
इससे मेथड सेम होगा दोनों J minus का J minus का.
क्या
मेथड सेम होगा J minus ट्रांजिशन का.
मेथड क्या
फिजिकली जिस तरह करेंगे.
फिजिकली तो हम कोई बात नहीं करेंगे ये ट्रांजिशन कैसे हो. ये तो एक ऑपरेटर एक्ट हो रहा है. ठीक है. Now these are the states in the coupled basis. They must correspond to some states in the uncoupled basis, right? Now if I look at this state, and I would like to write all of these coupled states in the form J1, MJ1 crossed with J2, MJ2. Okay, what do I need to do? हम ये टेबल बनाना कंस्ट्रक्ट करना चाह रहे हैं जिसका हमने ये वाला टेबल कंस्ट्रक्ट किया. ठीक है. I want to express the coupled basis states in the uncoupled basis in the direct order basis. Now this value of mj is the maximum possible for this value of j. So this is the maximum possible value of mj, and this maximum value of mj is achieved when each of the individual components have their mj's maximized. Now, which means the maximum possible value of mj for the first particle is 3 by 2, and for the second particle is 1. Yeah, but no, this is sorry, मुझे बहुत बड़ी I'm so sorry. मुझसे गलती होगी, मेरे ज़हन में कुछ चल रहा था. The first is a spin 1 particle. The second is a spin half particle.
So, but J is the summation of J values.
J is 3 by 2. J is 3 by 2. I have spin 1,
I have a J1 is 1, J2 is half. So possible values of J are 3 by 2 and 1 by 2. Okay, that's fine, that's fine. So MJ1, what are the possible values of MJ1? 1, 0 and minus 1. What are the possible values of MJ2? Half and minus half. So this maximum value of Mj for the total angular momentum can only be achieved when Mj1 is maximum and Mj2 is maximum. That is, this is 1 and this is 1. So this straight away corresponds to 1, comma 1 direct product with half, comma half. Okay. So this maximal state, which has a maximal value of Mj, which is also called a stretch state, straight away corresponds to the corresponding direct product state with no coefficient. The coefficient is just 1. Okay. Likewise, if I take this state, which is the maximal state, with the minimal value of total Mj, this can only correspond with 1 minus 1 crossed with half minus half. Remember that in this nomenclature, this first label corresponds to J1, this corresponds to Mj1, this corresponds to J2, this corresponds to Mj2. So this is the labeling scheme. This is J1, this is Mj1, this is J2, this is Mj2. Now what I would like to find out is how do I express this coupled state, which is an eigenstate of all 4 of these observables and is not an eigenstate of J1, Z and J2. How can I express this as a linear combination of the direct product states? Right? This is what I would like to do. So what I can do is the following. I can have the J minus operator act on this state. Let's see what happens. If I have the J minus operator act on 3 by 2, 1 half, I get 3 by 2. I get H bar 3 by 2 plus 1 minus 3 by 2 Mj minus 1, 3 by 2 minus 1 under root 3 by 2 1 half, right? The formula is for J plus minus acting on J and J is H bar J plus 1 minus Mj plus minus 1 under root J Mj plus 1, right? So I can use this formula that is already right somewhere. So this becomes H bar 3 by 2 by 2 by 2 5 by 2 15 by 4 minus 3 by 2 2 by 2 minus 1 by 2 is 3 by 2. So this is 15 منفی 3 12 12 बटा 4 under 3 H bar 3 by 2 1 half. So I made the J minus operator act on this state and I have received a state that is proportional to what I would like to achieve. Okay. Now I can also make the J minus operator act on this state. Okay, it's going to yield the same result. Okay. Let's have the J minus operator act on this state. Now if J minus operator is really J1 operator minus plus J2 minus acting on 1 1 cross with
Now first of all, J1 operator acts on this direct product state. Okay, and I use the same formula. But when the J1 operator acts on this direct, nothing, it does not touch this state. The second part. Okay, now J1 is acting on this. So H bar, J is 1, 1 plus 1 minus 1, 1 minus 1 under root the entire 1, 0. Nothing happens to the second half, right? Now I have J2 acting on this state. J2 acts on this state. I get value J is half plus 1 minus Nj is half minus 1. Nothing happens to this state. I get 1 crossed with half minus half. Now if I look at this is simply under root 2 and this is 3 bata 2 3 bata 4 jump 1 bata 4 this is simply 1. So this means that this particular expression that I am put in a triangle sign is really equal to under root 2 H bar 1 0 crossed with half okay, plus under root H bar H bar 1 1 crossed with half minus 1. But this must also be equal to what we found out from here under root 3 H bar, which means that if I take under root 3 to this side, I cancel out the H bar, I'm left with 3 by 2, 1. So I can complete this entry in the table. What I have, this state is really equal to 1 over under root 3 times 1 0 crossed with half plus 2 over under root 3 1 1 crossed with half minus half. So what I've done here, this coupled basis state, right, which is also happens to be an eigenstate of an interaction Hamiltonian of the type J1 dotted with J2, can be expressed as a linear combination of the direct product space. Okay. Sorry? कैसे switch होगी? ये देखो ना, ये है अंडर रूट 2. अच्छा अब देखो, ये वैल्यू है mj is half. Now look at this term. This term has j. This j is fixed at 1. This j is fixed at half. You can't do much about it. But you can choose combinations of mj1 and mj2 so that their sum adds up to 1/2.
So this 0 plus half is this half. Another possibility is that this 1 and this minus half adds to give you 1 half. So you just, by inspection, you can just pick up those direct product states in which the mj's have the proper value. So you can pick up this mj and this mj. So this is one possible combination. The first labels in these direct product states are fixed at j1 and j2. So you can just pick up the value of mj1 and mj2 such that they combine to give you the correct mj. Because in this total angular momentum state, the z component of the total angular momentum is always equal to the z components of the direct of the sums of the individual particles. In other words, now this state is an eigenstate of Jz, but this Jz is really J1z plus J2z. Now J1z, this state happens to be an eigenstate of J1z, and this state happens to be an eigenstate. Both of these states are eigenstates of J1z and J2z, even though the combination isn't an eigenstate. Remember this. So that is why you can choose the proper values of mj, so that you don't have to choose the other direct product state, because there are 6 possible product states. Just choose two of them. Okay. However, these coefficients have to be explicitly found. Okay, and these coefficients are called the Clebsch-Gordon coefficients. Clebsch-Gordon coefficients. Likewise, you can repeat the entire procedure. Okay, you can repeat the entire procedure for this state. You can have the J minus operator act on this, the J minus operator act on this state, and you will achieve your desired result. And let me state that result. Okay. So let's first choose the product states we choose. Right. This is minus half. So one possibility is that I have 1 0 half minus half. Okay. Or I can have I1 1 I minus 1 and half 1, right? I can have this state, and or I can have 1 0 crossed with half minus half, and I have to find out these Clebsch-Gordon coefficients. And if you repeat the same procedure, the Clebsch-Gordon, this turns out to be 1 over under 3 and plus 2 over under 3. Okay. So I can find out all the representation of the coupled basis states in terms of the uncoupled basis, remaining within the same J manifold. Now, at the top, the 4 rows are in the same value, with the same value of J. So I am not stepping out of the J manifold, because the J minus operator cannot change the value of J. It can only decrement the value of Mj. Likewise, I could have started off with this and have the raising operator act on the states. Now, how do I find out this state? This state, if you notice, if you compare this state with this state, these states have the same value of mj. So they must comprise the same combination of the direct products. Okay. However, the two states must also be orthogonal to one another, because they are basis states. Right? So I just choose the same direct product states, 1 0 crossed with half half and 1 1 crossed with half minus half, and choose my coefficients such that this state remains orthogonal to the state in the second group. So one possibility, now I can choose the coefficients non-uniquely. There is no one way of choosing the coefficients. That's why different authors come up with different values for the Clebsch-Gordon coefficients.
Just like here, I could have chosen a minus sign here and a positive sign here. So one possibility is that I make this minus 1/3 and I make this plus 2/3. Okay. And then I can have the lowering operator act on this state to find the corresponding direct product decomposition, or I could choose this state and write an orthogonal state that is orthogonal to the one above. Okay, so I can also choose minus 2/3, 1 minus 1 cross to half plus 1/3, 1 minus 1 cross to half. Sorry? कौन सा ये चीज ऐड हो गई ये टोटल आपका जे की दो पॉसिबल वैल्यूज हैं 3/4 हाफ इस जे के साथ ये एम जे की वैल्यू तो आप इन जे को क्यों ऐड करें क्या रीजन है जे को जे को ऐड करने कोई रीजन नहीं है आपने सिर्फ ये देखना है ये जो एम जे है ये इन एम जे से कॉम्बिनेशन से आएगा -1 प्लस हाफ इज -हाफ फाइन -1 इन जेस को क्यों ऐड करें no point in adding these days to get this. You just have to look at the the projection along any axis, which is the z-axis in our case. So these coefficients that we found here are called the Clebsch coefficients. Okay, and there are tables that are available. And in the book that I shared with you, as well as in the I've also uploaded a table of these coefficients on the website. Let me just draw one sample table for you. So if I would like to write, if I have a 1 cross half system, it means that J1 is 1 and J2 is half. So I have a 10 nucleus with a spin half electron. The table looks like the following. M1, M2, JM, and then you have the coefficients. The coefficients go in here. 1, 0, 0, 0, 0, 0, 1, 3, 2 over 0, 0, 0, 0, 0, 2 over 3, 1 over 3, 0, 1, 0, 0, 0, 0, 2 over 2, minus 1 over 2, 0, 0, 0, 0, 0, 0, 1 over 2, 2 over 3, minus 0. So this is a typical Clebsch coefficient table, in which if you would like to find suppose this j and j state, right, which has a value of j equal 3 by 2 and mj is minus half, which means you would like to find out this state. You will just pick up the collapse coordinate coefficients from this column. So there will be no combination of these combinations, no coefficient from these combinations of mj's, but there will be combinations from 0 minus half, because these add up to give you minus half, and minus 1 plus half, because this adds to give you minus half as well, and the coefficients will be given like this. Okay, so there are huge tables available, and there are computer programs that can find out these tables. Okay, but the proper point is that you should be able to derive these collapse coordinate coefficients. And remember one thing, if I have the direct product state, now going from one basis to another is simply a basis transformation. So I can write a similarity matrix which comprises the collapse coordinate coefficients, go from one uncoupled basis to the coupled basis, and go from the coupled basis to the uncoupled basis. That's easy to do. Okay, so now one last thing, last couple of minutes, if I have the state j and j, okay, I can write this state in the following fashion. Right? J and j. There's no harm in doing that. Now this identity is basically, I can expand, since the direct product states also form a basis for the Hilbert space. So I can expand this identity in the following fashion. J1 mj1 cross with j2 mj2, j1 mj1 j2 mj2, right? Sum over all possible values of mj1, go from minus j1 to plus j1, and mj2, which go from minus j2 to plus j2, acting on jm. So I'll replace the identity operator by this sum of outer products, because all of these states form a basis and they are mutually orthogonal. So I can do the decomposition of the identity operator in terms of this outer product which span the entire Hilbert space, where mj's take on all possible values. Correct? So I can write this expression in the following fashion now. Jmj is basically equal to, so I can find out the inner product of this cat with this bra, and I can write this cat on its own. So I can have J1 mj1 cross with J2 mj2. Okay, I have this cat, and my inner products, which are the scalar coefficients of these cats, are simply the inner product of each j and j, which is a coupled basis state with J1 mj1 cross J2 mj2. Right? So these are the coefficients, and I have to sum all of these over all possible values of mj1 and mj2. Okay. However, since mj must be the sum of mj1 and mj2, most of these terms will be 0. Okay? And in other words, I effectively need to sum up only over those terms for which mj equals mj1 plus mj2. Because for all other terms, these inner products are 0. And these terms, which are just scalar, these are called the Clebsch-Gordan coefficients. So what I've done is I've expressed the coupled basis state as a sum of direct product states, and the coefficients are called the Clebsch-Gordan coefficients. So these coefficients are denoted in J1, J2, J, and J1, M, J2, M, J. So these are just the Clebsch-Gordan coefficients which are write this. Okay, so this is an analytical expression for the closed coordinate positions. Now in the recitation today, there will be a discussion on the spin-orbit interaction, in which the spin of an electron interacts with the orbital angular momentum of an electron. And please do the homework. I carefully crafted the homework so that you can understand what's going on as far as this addition of angular momentum